So, hello again for the second part of MLTrain today. I hope everybody enjoyed the ESL guys. It was wonderful. And now we are coming back from an even better and more exciting session full of fire. So I want to thank Eli Bingham, who didn't take an Uber. He actually drove all the way here. He could have done that. We're going to spend the next almost 3 hours with a break. Let's welcome him. So since we're recording this, if you have any questions, just wait for me to come with the microphone so we can get it on.
Yeah, and feel free to interrupt with questions at any time. So this is supposed to be pretty interactive. All right. So welcome and thanks everyone for showing up for this kind of marathon tutorial. I hope it ends up being worth your time. In this first session, I'm going to talk to you about the basics of probabilistic programming and probabilistic programming in Pyro. So first, I hope to convince you that probabilistic modeling is sort of the right way to do things in AI and machine learning. I'm going to show you some really cool cutting-edge research that I think bears that out. Then I'm gonna try to convince you that the right way to do probabilistic modeling is to do it with a probabilistic programming language, and that Pyro is the right probabilistic programming language to do that with. Then we're going to learn how to actually use Pyro. We're going to build a couple of extremely simple models and learn the basics of Pyro syntax, which is just Python. And finally, we're going to see how to fit Pyro models, probabilistic models, to observe data. Because if you couldn't do that, then probabilistic programming wouldn't really be very useful. And for those of you who want to follow along with some material on your laptops, this material is drawn from the language introduction tutorials on the Pyro website. It's pyro.ai. Okay. So, like I said, I told you I was going to show you some cutting-edge research that I just think is really cool and to me is a really compelling case for probabilistic modeling in AI. So here, this is from a science paper in 2015 from Josh Tenenbaum's group at MIT, from his student who's now a professor at NYU, Brendan Lake. They built this really cool structured probabilistic model of handwritten characters as drawn by people. And the model encodes these motor programs, which are these kind of directed strokes that you see here on the right. And the cool thing about having such a rich structured model of handwritten characters like this is that you can do really powerful sorts of inference and generalization. You can parse images of characters into interpretable programs that generate new examples. You can learn to generate entirely new classes of characters from a single example. And the characters that you generate are actually in the experiments that they did in the paper. Kind of the killer experiment showed that the handwritten characters that they were able to generate fooled humans, human mechanical Turk workers, sort of the majority of the time. Another, I think, long-standing sort of open problem in AI research and in cognitive science is centered around this idea of vision as inverse graphics. That is the idea that graphics works by taking we get images from the world by taking 3D scenes, 3D models of scenes, just like you would have in a game engine, and running them forward through a renderer to project them onto a camera. And the idea then is that vision is the inverse of that process. That we invert the internals of the renderer and produce 3D scenes from images. And this is obviously sort of fraught with computational challenges and details that make or break things. But this is another paper in Science from this year from a group at DeepMind who built a really powerful generative model of 3D scenes built around some deep neural networks and some other things. And it's able to do, again, the power of doing vision this way is that you're able to do really, your models are able to do things that if you were just sort of directly trying to solve a problem, you wouldn't be able to. So for example, they're able to generate images of scenes. If they have an agent walking around in a maze, and they're able to generate images of scenes from previously unobserved viewpoints. The agent's able to imagine itself in another position and imagine the world as it would be if it were there. Along similar lines, not only is there this long-standing idea of vision as inverse graphics, there's also again in cognitive science, there's this idea of that people have intuitive physics engines in their head, right? So like if I were to throw a football at Nick in the front row here, he would probably know this and stick his hand up and put it in the right place to catch it. And one of the most promising explanations for why he'd be able to do that is that he actually has a model in his head that's simulating the trajectory of a football that I throw at him, and he's able to use that to put his hand in the right place to not get hit in the head. And these guys in this paper or in this line of work have actually sort of reified this idea, right, in software. They built an intuitive physics engine, evaluated it in predicting human judgments. It's actually a little rigid body physics engine that models things like blocks sliding down planes, and it does a great job of predicting people's judgments, both their really impressive judgments and the ones that they don't do so well on, which suggests that it's really capturing something fundamental about the way that people are performing physical tasks and representing physical knowledge. Finally, to close with an example sort of closer to machine learning, or maybe closer to practice. There's a group at Cambridge, or I guess who were at Cambridge, who've been working on this project called the Automated Statistician, and they want to put us all out of a job. The idea is that you actually write a model of let's say, sort of data science models that you can search through in a structured, and interpretable way, and they're able to exploit this internal structure and actually generate not just predictive models of time series. For example, I think in this report they're doing in this example they were doing something with solar flares, but they're able to take the structure and generate entire reports and descriptions of the data. And all these models are really complicated and domain specific, but the way that they're fit to data and the way that the principle that underlies them is all the same. It's the principle of the rules of probability, right? So all of the complicated computations that they're doing to fit these models to data can be boiled down to approximating these two or three things here. The sum rule, which tells you how to get a description of one thing from a description of two things, and the product rule, which tells you how to get a description of two things from two different descriptions of one thing each. And finally, Bayes' theorem here on the bottom left, which is the combination of all of these things, or the combination of these two rules, the sum and the product rule. These three ideas, right? These three mathematical rules and approximations thereof are sufficient to mathematically describe all of the computation that's going on models that I just showed you are being fit to data. Probabilistic programming languages, then, the reason we're all here, reify these ideas in software. That is, they take the rules of probability and they put them into a high-level programming language in an approximate form. So probabilistic programming language, PDLs like Pyro, the one I'm going to talk about, all have sort of a basic recipe, a basic construction. There's a nice high-level programming languages, like a nice high-level programming language that the thing is embedded in or built on. In Pyro's case, it's Python. There are others like WebPeople, which is built on JavaScript, or Church, which is built in Scheme. There are primitive random objects, distribution objects. There's extra pieces of syntax that mark when you're calling random functions. And there are primitives that allow you that allow data to modify the way that a probabilistic model runs forward. And of course, there's inference, which is what we're going to, which fits some of the sample statements to values of the others. So why aren't we doing everything already? Why aren't all of those models that I just showed you, all this cutting-edge research, why isn't it already happening in a probabilistic programming language? And I think as someone building these sorts of systems, it seems to me that there are two sort of major challenges, which in some sense are kind of generic and appear in any sort of complex software design problem, right? So on the one hand, we have the problem of scalability, right? So models, for example, the rendering engine, right? Vision's inverse graphics requires working with images and 3D models, right? And inference in models that have very large pieces of data or data structures internally requires high performance algorithms and computing systems that underlie the implementations of those algorithms. But on the other hand, these two are always in tension. There's the problem of flexibility, right? Those models are complicated, and it's often the case that taking inference algorithms, the sorts that you would find in your statistics textbooks off the shelf, those don't work so well. They don't scale so well, or maybe they don't even converge for whatever reason. And so you need a system that you can modify to fit the behavior of your complex probabilistic model as necessary. And I claim that Pyro is a partial answer to it resolves the tension between these two opposing attributes in a way that's most favorable for building systems like that. It's expressive. Probabilistic models in Pyro are functions with arbitrary Python code, including any sort of control flow you could want. There's some extra syntax. Pyro is scalable thanks to modern, thanks to the latest and greatest research in approximating probabilistic inference. Published at conferences like UAI. You should all go learn about what's up after today if you have a chance. And finally, Pyro is flexible, which I think is a thing that it does really well. And I'll hope in the course of this entire tutorial to kind of get you in the mindset of working with of this kind of flexibility, of how you can build a model and then build an inference routine around it to suit your needs. So let's dive right in. Now that I've kind of given you my sales pitch, let's dive right into the sort of nitty-gritty details of what probabilistic programs actually are. So here I've just written a Python program with a call that's simulating, let's say the reading on a thermometer, right? So the idea is that if it's cloudy, then the average temperature is probably lower, and the temperature that we sample at the end should reflect that. And if it's not cloudy, the temperature will be higher. in the sky, it could still be freezing. So that was just a regular Python program with a couple of calls to some objects from the PyTorch distributions library, or SciPy, or sort of pick your favorite library of probability distributions and samplers, random number generators. So Pyro code is just pretty much exactly that same Python program, except that the stochastic function calls, the calls to the random number generators, are wrapped in this pyro.sample primitive, and they're marked with names. Otherwise, this program is pretty much the same. Pyro programs are just, like I said, they're just like regular Python programs. They can be composed freely as long as the names of the sample sites are unique. So here you can see we're actually calling the program we wrote before, weather, which simulates the reading on our thermometer, to build this model of possible ice cream sales. So if I'm running an ice cream stand, then I might want to use the thermometer to I might want to know, what the weather's going to be, or I might want to look at the thermometer to decide, for example, how much stock I'm going to put in my ice cream stand that morning. Okay, so I've shown you the basics of building models in Pyro, which really is about as simple as you would expect. Or about hopefully as simple as I promised. Right? You take a regular Python program, and some of the function calls you wrap with this little pyro.sample method, or pyro.sample function, and you tag it with a name. And now I'm going to show you how to constrain Pyro models to data, and how to do inference in those models. How to work out the distribution of how to work out how likely it is that it's actually cloudy, given that you observed 55 Fahrenheit on the thermometer. And I'm going to do that with this even simpler example of attempting to weigh fruit with kind of a rusty kitchen scale, a noisy scale. So in this example, right, imagine that you have a kitchen scale like the one in the picture here, and when you place the same piece of fruit on it, it keeps giving you different numbers. But maybe you're attached to the scale, or you're just cheap and you don't want to get a new scale, and so you still like to use your kind of broken scale. And so you write a little Pyro program that describes your belief about how the numbers on the little screen on the scale pop up when you put the fruit on. And in this case, we're saying that we make a guess, and the weight of the fruit, the true weight of the fruit, is distributed somewhere in the neighborhood of that guess. And the scale then returns some noisy number which is centered at the true weight. So how would we actually use our super simple kitchen scale model here to weigh a piece of fruit, right? That is, we put the apple on the scale. We get out a number. Say we guess. We get out the number 9.5 grams, or ounces, I think. Yeah, ounces. 9.5 ounces for this apple. And we'd like to know what the distribution over possible weights is, given this observation of this random measurement. And there are two ways to express that you observed that one of the pieces of randomness in your Pyro program is fixed to a particular value. The first is to tag the sample site with this little obs keyword argument, which will have that sample site, the return, the value of that Pyro.sample measurement. You call that in the program. That will return the value 9.5. And there's also, if you as part of the sort of probabilistic programming design principle of separation of concerns, you'd like to separately specify your model and your data. Pyro also has this Pyro condition object, and so you can see that one of the reasons that we have names, the reason these sample sites are tagged with these strings, is that it allows us other functions. For example, here the Pyro condition to refer to those names without, say, directly having access to it allows programmers to refer to those names without directly having access to the running program. And those two have the same behavior.
What is scale in this example?
Scale
In
in the bottom one.
yeah.
That's this model that we wrote here.
Ah,
Yeah. So we just applied Pyro condition. So the question was, what is scale in the bottom example, the second piece of code here? And the answer is that it's this scale probabilistic program that we defined as our generative model of how the numbers appear on the screen.
Can you condition on functions of the sample or just named variable?
The question was, can you condition on functions of the variable or just the name variable itself? So you can build, you can actually always, you can add a new random variable into your model and then condition on the value of that. And that would be equivalent. But right now, because Pyro is designed to be practical with kind of the suite of inference algorithms or techniques that we've chosen, we restrict, we tend to prefer writing models so that, well, we prefer a condition on sample size rather than adding things into the model. But syntactically, the answer is yes, you can only condition on.
You also have a prior. You also have a prior on the. You also have a prior on the weight, and the guess, right?
That's right. So we're making a guess. We guess the weight of the apple.
Right. Is it possible for you to say specify a model with no prior, but actually do some kind of a max end kind of stuff?
Well, you could. So sort of more philosophically, perhaps, to answer this question in a slightly different way. When you write a probabilistic, a generative model, a probabilistic program in a language like Pyro, what you'd like to describe is what you'd like the model to sort of represent or to reify is your knowledge of how all of the variables and eventually the return value were produced. And so if you can write your model as a if you can work out the max end distribution for the weight prior, then you could replace that normal there. So you have to do it yourself, I guess, is the answer. And so then, having shown you how to constrain some sample size to data, can finally sort of turn to the central question in probabilistic inference and probabilistic programming, which is inference. Inference algorithms in Pyro and in other languages compute the distribution of sample sites that have not been constrained, given all the ones that have been. So in this case, I'm just showing you the simplest possible inference algorithm, which is applied to our scale example, conditioned on observing a single measurement of 9.5, which is important sampling or likelihood weighting from the prior, important sampling from the prior. And we're using these two simple inference algorithm, or this simple inference algorithm, then is to compute the distribution over weights, and then we're reifying it as another primitive distribution object.
So where does 8.5 come from again?
8.5 is our guess for the weight of the apple.
Oh, it's a guess.
That's the guess that we're using throughout. We think that the apple weighs 8.5 ounces. Having done this.
So how is this affected if you put like 2?
Well, so if you this histogram here, you can see that even though our guess was 8.5, the center of the mass there is at is sort of closer to the measurement at 9.5. And if you guess 2, right, then the histogram that you get out at the end would be sort of, because that prior is further from the true weight distribution, or the weight distribution given the observation. You'd see a center of mass, which is you'd see a distribution with a center of mass that's closer to the closer to the 2 than it would be if you guessed 8.5, and you'd see it be much wider, much more dispersed, because you would be more uncertain. So you might want to, if you guessed 2 and you got 9.5, then you might want to collect more measurements to try and squeeze the result, the posterior distribution.
So you're saying that we would need more iterations to converge to the true value?
Right.
More samples, okay.
Yeah. Here we just kind of got lucky, right? Because we did a good job guessing the weight of the apple. But so there are lots of ways. There's a whole sort of zoo of ways of doing exact and approximate probabilistic inference in probabilistic programming systems. But in Pyro, we're sort of focused on, although we've implemented several, we're focused on really kind of a simple idea, which is that we're going to do inference by building models of the posterior distribution, the distribution over the unconstrained sample size given the data. So we write another Pyro program, which we'll call a guide program, which may contain a bunch of other code, but must contain a Pyro sample statement for every unconstrained sample statement, in this case weight, which appears in our model. So our scale model is so simple that the true distribution over measurements, over weights given measurement, can actually be computed by hand if we were to write this down and do some math. Here I've written a guide program, a model of the distribution of weights given data, which is the true posterior distribution. So sometimes you can do this, right, and it's great. It's you now have the object that you were after in its sort of most useful and general form, which is a generative probabilistic program that you can compute things from. So that guy, for example, estimates the distribution over weights given measurements directly. Here you can see we have a pretty similar histogram to the one that I showed you before, where now the distribution of having guessed 8.5 again, the same guess that we've been using for the weight of the apple. We can see now that having observed 9.5, as we did before, that if we keep running this guide forward and draw and build a histogram of the return values, then we see again a sort of thin distribution centered around the true the true weight of the apple. Unfortunately, in pretty much any model of interest, the true distribution, the true posterior guide, the one that actually describes the distribution of all of the sample sites, all of the unconstrained sample sites, given all the constrained ones, we can't actually compute that by hand. If we could, then we wouldn't need probabilistic programming. So here I've written the scale, the same scale model that we've been using, and I've written one below it, which is now intractable. That is, we can no longer compute the true posterior, the true guide, the ground truth posterior distribution by hand. Anyone spot the difference?
Can you use of fn from the second one, the function?
That's right. So basically any nonlinear function that we put there between the weight and the measurement will mean that we can no longer compute this lovely ground truth guide that we did, on a whiteboard somewhere and wrote as a probabilistic program. We can no longer do that. So now we must resort to approximations. And again, kind of in keeping with our philosophy of inference, of doing inference by building models of the posterior distribution, in Pyro, rather than guessing a single guide, we could guess an entire parameterized family, and then use we could leave some of the spots in the guide program, some of the values that are free for an inference algorithm to fill in, an optimization algorithm to fill in. And we do that with this second Pyro primitive piece of syntax, pyro.param, which takes again a name and then a value, which is the parameter value, the thing that the value that sort of indexes along your family of possible guide programs. You can see here that now in this guide, in this model of our distribution of weights, the distribution over weight could now vary freely, or could now be adjusted freely according to the values of these parameters, which are exposed to inference algorithms. And so, to actually to find the right values, or to find values of the parameter that are of the parameters of these holes in the program that we could fill in, that are close to the ones that we the ones that we'd get if we could actually write the true posterior. We're going to optimize those parameters with respect to a loss function, some function that measures the closeness between the true posterior distribution and a member of our parameterized family of guides. So in Pyro, we do that with this sort of syntax and this pyro.infer.sci object. So we search for the best guide by optimizing our parameters with a loss function. And the optimizer that we're going to use is a light wrapper. So Pyro is built on PyTorch. All of its primitive distributions and inference algorithms use PyTorch's math, GPU acceleration, automatic differentiation, all that sort of thing. The optimizer here, the thing that's going to actually fill in the holes in the program, is just a thin wrapper over a PyTorch stochastic gradient optimizer. Here you can see if we create this SVI object. SVI stands for stochastic variational inference. You don't have to worry about what that means right now. We'll come back to that. But it effectively means inference by optimization. We pass it as we did before with the important sampling object, right? We pass it a model with some of the, in this case our scale model, with some of the measurement site constrained, or some sites constrained. We pass it the parameterized guide that we wrote, this guy, and an optimizer, and a loss function, which again I'll talk about in more detail in the next tutorial. And then all we have to do to optimize the parameters with respect to this loss function is call svi.step. So this object has a step method. You pass in some data, you repeatedly call step, and it takes a single gradient descent step on the parameters. You can see here that this loss function is, since it's this is a function that we want to maximize. So here I plotted it going up. And what this nice this nice abstract idea of this family of possible guide programs circumscribed by this region of sort of admissible programs, or you know, the space of all possible programs. One way that we can change the sort of the curve around one way that we can change the shape that we've drawn around the set of possible guide distributions, this green thing here, or prevent our optimizers from coloring out of, you know, going out of the lines and running off into the gray area, are with constraint objects. So Pyro's distributions, just like the optimizer and math, are built on top of PyTorch, particularly the torch distributions library that the Pyro team did a bunch of engineering and contributed upstream for. And here, so you can add that torch distributions library comes with some constraint objects that allow you to force some parameters to stay within certain regions. So here, because this parameter b is the variant, the standard deviation of a normal distribution, it has to be positive. Right? So we're going to use a positivity constraint to force it to be positive. This is kind of enforcing these kinds of things is a huge pain. If you've ever written if any of you have ever written inference algorithms for yourself, you know, for problems sort of in a bespoke way, especially if you use variational inference, you probably come across, you know, you probably found it maddening to keep your optimizer or your inference algorithm from going out of bounds. So that's just an example of the kind of convenience that we've tried to build in as we build Pyro around inference optimization. So if we just revisit our design principles that I described to you at the beginning of the tutorial. Why build Pyro around inference optimization? Why does it meet these principles that we set out in the beginning? How does it resolve these constraints? Well, it does so in these in the following ways, right? So one, we can express very rich models. We're no longer constrained by needing to know lots of integrals by hand. We don't need to know them by heart if we want to do variational inference. These algorithms are also highly scalable, both to large models and to large data sets. Gradient-based optimizers, if you've all ever done ever played around with deep neural networks, deep learning, you know that you can optimize, you can do a reasonable job of optimizing over absolutely enormous configuration spaces with gradient-based optimizers. And stochastic optimizers like the PyTorch SGD that we used to fit the parameters for the guide for our scale object, our scale model. Those work with mini batches both of data and of latency, so we can update our parameters, our belief, our posterior distribution without without putting the entire data set of the entire model into memory. Which means that in principle, at least, we can work with arbitrarily, just as you can with deep neural networks, you can work with arbitrarily large models or data. And finally, guide programs are flexible, right? They offer a large surface area for incorporating knowledge about how inference should work, right? So in our scale guide, right, we added this positivity constraint, and we also we forced the approximate distribution to be a normal distribution. And similarly, since these are just again, these are programs. We have a lot of tools. You know, we can reuse all of our existing tools for troubleshooting software failures or statistical failures.
Can I ask you a question? What kind of constraints can you enforce? For example, can I say that the weight of the apple should never be, you know, bigger than the diameter of the apple? let's say I was measuring both of them, and I want to put a constraint between two variables. Is there any limitation to the number of constraints?
So this kind of relates to the question that the gentleman behind you asked at the beginning, which was, or closer to the beginning of the talk, which was, how can I place constraints on things that are example statements? And the answer that I gave was, or that are more complex than particular variables in the model. And the answer was that you can add another random variable to your model, which is effectively the probability of that constraint being true. And in that way, you can express arbitrarily complex constraints for your inference algorithms to satisfy. So here you write another sample statement. Say it was a Bernoulli distribution, whose probability of being true was whether that constraint was true, plus some noise or something. So I think I've run out of time here, just about.
We've got 2 minutes.
2 minutes? Okay, perfect. And so just to recap, I gave a sort of short whirlwind tour of some of the most exciting to me breakthroughs in AI research that are driven by where we made progress on these long-standing problems through building rich probabilistic models. I've tried to make the case to you that we should be doing this. We should be building models like that rather than building them as one-offs from scratch every time. Right? That some grad student writes and nobody can ever figure out how to use again. We should be building them with probabilistic programming languages. I explained to you how to build Pyro models up as Python programs with a little bit of extra syntax, and how to fit those programs to observe data using this sort of basic idea around which Pyro was built, inference optimization. In the next session, I'll give you an introduction to Bayesian machine learning in Pyro.
So when you use variational distributions to model your posterior, right?
Mm-hmm.
Let's say your data arrives in batches. So you got a bunch of data and then you pick your model. And
Right.
you got your variational distribution nicely estimated by optimizing. Now you got a new set of data. Do you have to go back and do the whole thing, or can you actually just update the variational distribution to the new family?
I think in that case you have to use you might have to use a different loss function if you want things to be approximating Bayesian updating, where you use the posterior as your prior.
Right.
But
Do you actually? I mean, is it a first class thing in Pyro, or?
you should be able to do that. We don't have that. We don't have like an example showing that. But yeah, you can certainly do that.
Are there any other questions before we take a small break? A few minutes. I think everybody's ready to dive in.
All right.
Okay, so let's thank 2-minute break, sweet guys.